This video, we're going to uh, cover suggested homework problems from 5.1. Just note up front that we're only going to cover selected sections of Chapter 5 for Calculus 1, and the other sections of Chapter 5 will be covered in Calculus 2. Let's start with some pre-calculus review of the natural log function before we get into differentiation of the natural log function. So these first few problems go back to transformations of the natural log function. Remember, the parent graph for the natural log function has a vertical asymptote at x equals 0 and has an x-intercept at 1, 0, and it is approaching. Let's see if I can draw this so that it's rising to the right from the vertical asymptote and goes through the x-intercept, and it levels off very quickly, but it doesn't have a horizontal asymptote. It just has a rate of change where it is increasing at a decreasing rate. I'll draw this on the calculator for you since it's better at drawing than I am. ln of x and zoom 6. And you can't see that asymptote very well, but it's there. It's getting closer and closer to x equals 0. So I'm going to clear that, and then I'm going to tell you what the right answer is, and then for these, just looking at it, and then I'll confirm with my calculator. So we have a vertical shift up by 1. So look at this point 1, 0 and shift it up to 1, 1. Which one of these has a point at 1, 1? It's going to be B, number 9. And let's graph in a different color here. ln of x. Close your parentheses. Don't put the +1 on the inside. Like that. And let's graph that and see how that is B that has been shifted up 1. The second problem here, number 10, is a vertical reflection. So start with the blue function, and everything that's negative becomes positive. So it's going to be coming down through 1, 0 and then kind of level out here. So which one is coming down through 1, 0 and then kind of leveling out? That's D. The third one, let me show you this one here. Negative ln of x, like that. And then we have ln of x minus 1 in parentheses, so that's going to shift 1 to the right. So we're going to have a vertical asymptote at x equals to 1, and our x-intercept will be at 2, 0. So x equals 1 with an x-intercept at 2, 0, that's A. So y equals ln of, and in parentheses, we have x minus 1. That's our horizontal shift there. And there's our magenta 1 there. That's number 11. See how it shifted over to the right. And then our last one is going to be both a horizontal and a vertical reflection. So we should have our asymptote at x equals to -1, and this should be going from the top of the asymptote down through -1, 0, down and to the left. So that is C. And last one here, negative ln of negative x. It's going to have that vertical asymptote there at 0, and it's going to pass through -1, 0, and it's going to be rising to the right at an increasing rate here because it is the reflection both across the x-axis and the y-axis of our blue function. I'm going to clear all those things now from my calculator so I can use my calculator for other things. But hopefully that was helpful to you to see all those transformations happen with the calculator. Let's move on now to number 13. And we're being asked to sketch the graph of the function and state its domain. So I'll do a sketch and then I'll put it in the calculator since the calculator is better at drawing than I am. So 13 is f of x is equal to 3 ln of x. So we need to still pass through 1, 0, but we need to go down faster and we need to go up faster. So this is going to kind of be more like this, that it's going to be rising faster and it's going to be falling faster. It's going to still get towards x is equal to 0, but it's really stretched out here. So I might just see it going that way on my graph. I might not even see it level out yet when I graph this. So 3 ln of x. Okay, and it's starting to turn and level out a bit, but it's still taking a lot longer to level out than the original function did. And this is still going down and to the left here. Okay, so something like that. Let's look at number 19. Said, oh, I didn't find the domain of that one. For 13, the domain still would have been 0 to infinity, which is what the domain is for all log functions that haven't been shifted left or right. And its range, it didn't ask me about this, but its range is negative infinity to infinity. Again, we don't have a horizontal asymptote with log functions. We have a vertical asymptote with log functions. So it restricts the x value, but the y values remain unrestricted. All right, starting with number 19, they're going to give us some approximations for natural log of 2. I'm going to get back out to my home screen because I'll need this in 0.6931. And ln of 3, they're going to tell me is approximately 1.0986. And they want me to use some log properties to break these things down into their natural log components of that have arguments of them that are prime numbers. So for instance, ln of 6 is equal to ln of 2 times 3. And I have a log property that says ln of a times b is equal to ln of a plus ln of b. So we're going to break this up into ln of 2 plus ln of 3. And I'm going to add these approximations 0.6931 plus 1.0986. It's equal to 1.7917. That was part A. For B, we have ln of 2 divided by 3. So kind of the opposite of this one, that when I divide, I'm going to subtract the logs where the part that's in the numerator is the positive part, And the part in the denominator is the negative part, the part that I'm subtracting. So using that, this is going to be ln of 2 minus ln of 3. It's going to be equal to, let's change this to a minus sign, negative 0.4055. And then we have C is ln of 81, which is ln of 3 to the 4th power. So we have a log property that says ln of a to the n power is n ln of a, something like that. So we'll write this as 4 times ln of 3 is approximately 4 times 0.6931, and that's going to be 2.7724. Oh, I'm sorry, 3 to the 4th, not 2 to the 4th. 4 times 1.0986. Yeah, that's better. 4.3944. And for comparison, if you want to, let's see how close this is, since we're approximating 3944. That's good, right? That's good to 4 decimal places. So now let's look at basically same property here, but we have a square root of 3, which is 3 to the 1/2 power. So this is 1/2 ln of 3 is going to be 1/2 of 1.0986 is approximately 0.5493. Okay, moving on to number 21. Most of the time, we're not going to use approximation techniques like that. We'll just use our calculator. And it looks like the book usually wants us to go to 4 decimal places for logs, is what I'm seeing from that, unless they tell you otherwise. So we have ln of x divided by 4, and we're just going to use our log properties to expand this. We just talked about those log properties. Now the book will leave it like that. I'm not happy with that because we haven't broken this 4 down into prime numbers. So I'm going to write that as this, and then completely expand it to this, where I have prime numbers for my basis. Why am I doing that? Because I want to make sure that any of the parts, that if I have more parts that have common factors, that all of those things get combined with one another. Maybe they zero each other out in some way. I won't see that unless I break things down into prime factors, and most of the time that's what student solution manuals and answer keys and things like that are going to do. It's just best practice to break things down all the way, just like you write things in factored form when you deal with polynomials when you can, and things like that. It's kind of the same idea here of this is the way in which you've shown everybody that you've broken everything down all the way and combined everything that you can. So try and get those logs into things that have prime factors for their arguments if you can. So 23, prime numbers as their arguments. Ln of x, y over z I'm going to put lines through my z's. So this is ln of xy minus ln of z. And then xy, that'll break up into addition, ln of x plus ln of y minus ln of z. For 25, we have ln of x times the square root of x squared plus 5 is going to be ln of x plus ln of the square root of x squared plus 5. And I think that you saw in the previous problems that the square root is just a 1/2 power. So the 1/2 power can come out front. Ln of x squared plus 5. X squared plus 5 does not factor anymore. I can't break that down. So I'm going to leave that just like that. 27 says ln of big square root 1x minus 1 over x, like so. So the biggest thing going on the outside is that 1/2 power, so I'll take care of that first. And then on the inside of that, we're going to have ln of x minus 1 minus ln of x from that division. And I'll go ahead and I'll distribute that 1/2 over the parentheses, like so. In 29, we have ln of, and this should be in brackets here so that you can tell where the log ends. I don't like it when books don't put their logs in parentheses and just write them in italics or whatever and assume that you can see where they end. So let's make a good, set a good example and use our grouping symbols to tell everybody clearly what we mean to do, like so. And then bring this 2 down, like that. And that's fully expanded. Now we're going to go the other way and we're going to condense. And again, all this should feel like pre-calculus. You probably did this if you took 161 in the Virginia Community College system, then you should feel pretty comfortable with all this so far. So I see subtraction of logs, so that's going to turn into division. Here in 33, I have a 1/3 on the outside, 2 ln x plus 3 plus ln of x minus ln of x squared minus 1. I'm going to try to write it the way that it's shown here without distributing the 1/3 through. So I'm going to leave that last. And inside, I'm going to have a x plus 3 squared and an x in the numerator and an x squared minus 1 in the denominator. And then I need ln of the cube root of all this, x times x plus 3 squared over x squared minus 1. The only factors of x squared minus 1 are x plus 1 and x minus 1, and neither of those factors appear in the numerator, so there's really no need to break that down. You can if you want to. It won't help you simplify the problem at all. Let's look at number 35. For ln of 2 minus 1/2 ln of x cubed plus 6x. So we have 4 ln of 2 is ln of 2 to the 4th, which is 16, minus ln of the square root of x cubed plus 6x. This is going to be ln of 16 divided by the square root of x cubed plus 6x. Is 35. Let's look at number 39 now, which is a limit, and this has to do with that vertical asymptote that we saw. Remember that the vertical asymptote has only one side that we can approach from. If we try and approach from the other side, the limit's not going to exist. So we're approaching from the side here that has activity, ln of x minus 3. Let's take a look at what that graph would look like. 1, 2, 3, there's our vertical asymptote. 1 to the right of that will be 4, and that will be my x-intercept, and I'll be going this way and this way. So as I approach 3 from the right, I'm going towards negative infinity. Let's look at 45. Find the derivative of the function. Okay, so we have the derivative with respect to x of ln of x. That's going to be 1 over x. Let's throw in our chain rule since we know our chain rule now. What if I have derivative with respect to x of ln of u, where u is some function of x? So that's going to be 1 over u times u prime, or times du dx. So sometimes people will write this as u prime over u. Instead of 1 over u times u prime, it's the same thing. So let's look at 45 here. If f of x is equal to ln of x squared plus 3, my u is x squared plus 3, and my u prime is 2x. So we have f of x, start with f of x, is equal to ln of u, and f prime of x is 1 over u times u prime. It's 1 over u times u prime. So that's 2x over x squared plus 3. Let's look now at number 47. (47) is y equals parentheses ln of x raised to the 4th. So let's use a log property first to make this easier for ourselves. This is the same thing as 4. No, this is not the same thing as that. So u is equal to ln of x, and u prime is 1 over x. This is different than if I said y is equal to ln of x to the 4th, like this, and then the 4 could come down front, but this is not 4 x's, this is 4 of the ln of x's. So this is the chain rule. So we need to say that y prime is 4 parentheses ln of x raised to the 3rd times 1 over x. So y prime is 4 times ln of x raised to the 3rd divided by x. 49. Is y equals ln of t plus 1 to the second. So I can use a log property here to simplify y to be 2 ln of t plus 1. And that's helpful. So my u here is t plus 1. My u prime is just 1. So y prime is 2 times 1 over u times u prime. So y prime is 2 over t plus 1. Let's look now at 51. Says y equals ln of x root x squared minus 1. So I think it's easier to split this up and differentiate each of the individual logs here. So this is ln of x plus 1/2 ln of x squared minus 1. I could break that up a little bit more, but that's really not going to help me so much with this problem because I'm going to need to make a common denominator when I'm done. And might as well not try and do that with 3 denominators. So this is 1 over x plus 2, and then this is my u down here, and then my du is up here, and then not du, u prime. So u is x squared minus 1, u prime is 2x. So my y prime is 1 over x plus x over x squared minus 1, and x squared minus 1 over x squared minus 1, and then multiplied by x over x here. Y prime is x squared minus 1 plus x squared over x times x squared minus 1 is 2x squared minus 1 over x times x squared minus 1. F of x is ln of x over x squared plus 1. So f of x is ln of x minus ln of x squared plus 1. U is x squared plus 1. U prime is 2x. F prime of x is 1 over x minus squared plus 1. 2x, nothing cancels here. I do need to make a common denominator, so f prime of x, 1 over x times x squared plus 1 over x squared plus 1 minus 2x over x squared plus 1 times x over x. F prime of x will be x squared plus 1 minus 2x squared over x times x squared plus 1 is a 1 minus x squared over x times x squared plus 1. I prefer to write the positive part of my subtraction first so that it's not confusing as to whether that negative was meant to go outside the whole thing. If you want to factor a negative out front and write x squared minus 1, you can do that. The factors of x squared minus 1 are going to be x plus 1 and x minus 1. Neither of those factors show up in the denominator, so there's no reason to factor the numerator here. Let's look at 55. G of t is equal to ln of t divided by t squared. So my u is ln of t, and my v is t squared. My u prime will be 1 over t. My v prime will be 2t. G of t is u over v. So g prime of t will be u prime v minus v prime u all over v squared. So this is going to be u prime times v. T squared divided by t is t minus v prime u. It's going to be 2t ln of t over v squared will be t to the fourth. And I see a t that's common in everything. So I'm going to divide that out and make this 1 minus 2 ln of t over t to the third for my final answer. Um, look now at number 57. Y is equal to ln of x squared. So we can write this as ln of 2 ln of x, which is going to be y equals ln of 2 plus ln of x. When I use my log properties, and ln of 2 will just be a constant, and I'll only need to be concerned with this part right here. So u is equal to ln of x. U prime is 1 over x. So y is equal to ln of 2 plus ln of u. Y prime is 0 plus 1 over u times u prime. So y prime is equal to 1 over u times u prime is 1 over x ln of x. Looking at next problem here, 59. We have y is equal to ln of square root of x plus 1 over x minus 1. So y is equal to 1/2 ln of x plus 1 over x minus 1. Y is equal to 1/2 of ln of x plus 1 minus ln of x minus 1. And I can leave that with the 1/2 out front. Y prime is 1/2 of, and then this is going to be 1 over x plus 1 minus 1 over x minus 1. Derivative of this piece is 1, derivative of this piece is 1. So when we make a common denominator, we need to multiply the first fraction by x minus 1 over x minus 1, and the second fraction by x plus 1 over x plus 1. Y prime is 1/2 of, and then this is x minus 1 minus 1 dx plus 1. over x plus 1 times x minus 1. If you want to write that as x squared minus 1, you can. I'm going to go ahead and do that. Equal to 1/2 of x minus 1 minus x minus 1 over x squared minus 1. So that's going to make y prime equal to x minus x is 0. So this is 1/2 times a -2 over x squared minus 1. And this 2 goes into that -2, -1 times. This is -1 over x squared minus 1. And I'd like to make that -1 into 1 over -1 so that I can change this order of subtraction. Like so. Just don't like leaving negative signs if I can help it when I have subtraction of the problem, and I can change the order of subtraction. So less likely for somebody to come behind and make a mistake by missing the negative sign if I do that. All right, let's look at 67. And they want us to find the equation of the tangent line now. So we're given the function y is equal to ln of x to the 4th. Notice this is not wrapped in parentheses. This is the same thing as 4 ln of x. And they give us the ordered pair 1, 0 that's on the graph. They want us to find the equation of the tangent line to the graph of the function at the given point. So y prime is 4 times 1 over x, or 4 over x. Y prime at 1 is 4 over 1 is 4, so my m is 4. My equation of my tangent line is y minus y1 is equal to m times x minus x1. Y is equal to 4x minus 4 is the answer to part A. So let's graph y equals ln of x to the 4th. Zoom 6. Okay, there it is. Now, use the graphing utility to graph the function and its tangent line at the point. So, second, draw tangent at x equals 4, and there it is. And okay. And then I want y equals, and I want to graph 4x minus 4. Oh, I drew the tangent line in the wrong place. Second, draw, clear draw. Come in here. And second, draw tangent when x is 1. There we go. So my blue and my red lines lie over top of each other. And see it unless I See if I turn this one off and then turn it back on. We'll draw it. Second, draw tangent at 1. Y equals. And there it is. Okay. Same type of question here. Going to clear all of this. My drawing's gone, that's good. So 69 f of x is equal to 3x squared minus ln of x on the at the 0.13. So f prime of x is equal to 6x minus 1 over x, f prime of 1. 6 times 1 minus 1 over 1. 6 minus 1 is 5. So y minus 3 is equal to 5 times x minus 1. Y minus 3 equals 5x minus 5. Y is equal to 5x minus 2 when I add 3 to both sides. So this is y equals 3x squared minus ln of x. And then I want to second draw tangent at x is 1. And that's 5x plus a negative 2. Which is what I have, 5x minus 2. And then I want to draw 5x minus 2, which is the same thing, and it's right at the top of the tangent line. All right, 75. Logarithmic differentiation. I think this is really fun. This is going to be important, especially in Calculus 2 later. Do not forget this skill. So, but for right now, what's interesting about this is that this is one of the ways in which you can prove the product and quotient rules to yourself. And I think I mentioned back with the product and quotient rules to pay attention to the fact that the product rule was going to have a plus sign in it, and the quotient rule was going to have a minus sign in it, and it was going to have something to do with the properties of logarithms. So let me just stop and show you that right now, since that's kind of fun, and taken aside from the homework for just a second. So if I have y is equal to u times v, and I take ln of y is equal to ln of u times v, which is equal to ln of u plus ln of v, then if I differentiate everything, this is 1 over y times y prime. We're doing implicit differentiation here. Is equal to 1 over u times u prime plus 1 over v times v prime. And then I have y prime is equal to y times 1 over u times u prime plus 1 over v times v prime, and that y is the same thing as u times v. And so when I distribute through, The u's will cancel in the first term and leave me with v u prime plus, and the v's will cancel in the second term, leaving me with u v prime. And I think that that's the way that the textbook usually writes it. And I write u prime v plus v prime u and tell you that it's the same thing. But this is why they write it this way, is because they're using this logarithmic differentiation to get to it. And when they do that, they're writing their multipliers first because of this technique. Let's look now at the quotient rule. Y equals u over v. So ln of y is equal to ln of u over v is equal to ln of u minus ln of v. So 1 over y times y prime is equal to 1 over u times u prime minus 1 over v times v prime. And y prime is y times 1 over u times u prime minus 1 over v times v prime. So y prime is, and then y is u over v times 1 over u times u prime. I'm going to write that as u prime over u minus, I'm going to write this as v prime over v. And so the u is going to cancel in the first term here, and I get u prime over, and I'll write u before v. I'm sorry, u prime over v minus, and the v's will not cancel in the second term here, because this is in the denominator, this is v squared, and this is v prime u. So I need to make a common denominator here, v over v. So this is y prime is u prime v minus v prime u all over v squared. And all that should look familiar. Those are just like the proofs, if you want to say that, to the product and quotient rule that you can do after you learn this logarithmic differentiation technique. Let's go and apply that to some other rules, and we'll avoid using the product and quotient rule now by doing this logarithmic differentiation. So y is equal to x root x squared plus 1, x greater than 0, so ln of y is equal to ln of x plus ln of root x squared plus 1. So ln of y is equal to ln of x plus 1/2 ln of x squared plus 1. 1 over y times y prime is equal to 1 over x plus 2, and then this is x squared plus 1, and this is 2x. U is equal to x squared plus 1. U prime is 2x. So this is 1/2 of 1 over u times u prime, or with u prime in the top. So 1 over y prime was 1 over x plus 1 over 2, and this was 2x, and this was x squared plus 1. The 2's cancel and give me 1 over y prime is 1 over x plus x over x squared plus 1. And I might as well make my common denominator now. So this is x squared plus 1 plus x squared over x times x squared plus 1 is 2x squared plus 1 over x times x squared plus 1. And I'm not done because I still have y on the left-hand side. I need to solve for y prime. So this is y is x root x squared plus 1 times 2x squared plus 1 over x times x squared plus 1. So the x's will cancel, And then the square root will come out with the factor of 1 and leave me with a square root in the bottom. So this is 2x squared plus 1 over root x squared plus 1. So I've got 77. Y is equal to x squared root 3x minus 2 over x plus 1 quantity squared, x greater than 2/3 because of the domain of this square root part here. Notice this is very helpful when you have products of more than two functions, or you have mixtures of products and quotients and things like that. That don't fit nicely into either the product or quotient rule, that are only one thing times one thing or one thing divided by one thing. This is really helpful to get those things broken up. So plus ln of root 3x minus 2 minus ln of x plus 1 squared. So ln of y is equal to 2 ln of x plus 1/2 ln of 3x minus 2 minus 2 ln of x plus 1. So 1 over y times y prime is 2 over x plus 1 over 2 times 3x minus 2 times 3 minus 2 over x plus 1 times 1. Common denominator time, y times y prime, 2 over x times 2 times 3x minus 2 times x plus 1. At some point, I would just want to leave this, but I think your book is going to always put it all together. Plus 3 over 2 times 3x minus 2 times, actually, let's try something first before I do this. This is opposite of what I did last time, but let's try and move this over before I do anything, and let's see if some of the denominators go away. No, those already go away. This is a 3. Okay, so now let's see if I can simplify this a little bit. Y prime is, and one of the x's in the numerator in the first term will go away with the x in the denominator. And then we'll have square root down here. And this will be 3x squared left in the top. And then minus x plus 1 to the third. And 2x squared root 3x minus 2 stays. So awesome. So these two are already have like denominators. So let's get the rest of these. So I need to multiply the first and last. See, this one needs a 2. And it needs another x plus 1. And it needs a root 3x minus 2. And then this one needs another x plus 1. And then this one just needs to have a 2 and a 3x, root 3x minus 2. All right, so this is 4x root 3x minus 2 times x plus 1 this is plus 3x squared times x plus 1, and this is minus 4x squared times 3x minus 2, all over 2 times x plus 1 to the third times root 3x minus 2. So I see this is this should be 3x minus 2, because I already had a root 3x minus 2 and another root 3x minus 2 is 3x minus 2. So no more roots in my numerator. So let's see if I can do anything here. This is 4x times 3x squared minus 2 plus 3 is plus 1x minus 2 plus 3x to the third plus 3x squared minus 12x to the third plus 8x squared, 2x plus 1 cubed root 3x minus 2 is 12x to the third plus 4x squared minus 8x minus 9x cubed plus 11x squared over 2x plus 1 cubed root 3x minus 2. And then 12 minus 9 is 3x cubed. 11 and 4 is 15x squared minus 8x over 2x plus 1 cubed root 3x minus 2. I'll pull that x out just to show that well, they're going to leave it because the x doesn't cancel out with anything on the bottom, so they're just going to leave it. And that's what my dy dx, or my y prime, is equal to. So y prime is all of this. Look at 79. Y equals x times x minus 1 to the 3 halves over root x plus 1 and x greater than 1. So ln of y is equal to ln of x plus 3 halves ln of x minus 1 minus 1/2 ln of x plus 1, 1 over y prime is equal to 1 over x plus 3 halves x minus 1, 1, 1/2 x plus 1, 1, 1 over y prime equals let's see, we have a need for a 2, an x, and an x minus 1, and an x plus 1. Let's multiply by y and see what happens. So y prime is equal to x minus 1 to the 3 halves over root x plus 1 times 1 over x plus 3 over 2 x minus 1 minus 1 over 2 x plus 1. So this is y prime is x minus 1 to the 3 halves over root x plus 1 plus 3x times, and then x minus 1 will cancel out and leave me with a root x minus 1 over 2 root x plus 1 minus, and then this will be 2 x plus 1 to the 3 halves. This will be x minus 1 to the 3 halves. It's not really a lot simpler, but I need to multiply here by x plus 1 over x plus 1 for sure. And here by x plus 1 over x plus 1 for sure. Okay, and now I need to multiply here by 2 over 2. I think that gives me my common denominator that I'm looking for. So y prime is 2 times x plus 1 times x minus 1 to the 3 halves plus 3x times x plus 1 times x minus 1 to the 1/2 minus x times x minus 1 to the 3 halves over 2 times x plus 1 to the 3 halves. Now let's try and do some factoring here. Y prime is, let's pull out x minus 1 to the 1/2. That leaves me with 2 times x plus 1 times x minus 1. 3 halves minus 1/2 is 2 halves, which is 1, plus 3x times x plus 1 minus x times x minus 1. And that's going to be a lot easier on the inside there to deal with. 2 times x plus 1 to the 3 halves. This is y prime is x minus 1 to the 1/2. I'll make that a square root in a little bit. 2 times x squared minus 1 plus 3x squared plus 3x minus x squared plus x over 2x plus 1 to the 3 halves power. Y prime is, and then I'll write all this stuff first. This is 2x squared minus 2 plus 3x squared plus 3x minus x squared plus x root x minus 1 over 2x plus 1 to the 3 halves. And 2 and 3 is 5, minus 1 is 4. 3 and 1 is 4, and minus 2. So I have a common factor of 2 in that quadratic on the inside that I'm going to pull out because it will cancel out with the 2 in the denominator. And I'm left with y prime is going to be 2x squared plus 2x minus 1 root x minus 1 over 1 dx plus 1 to the 3 halves power. That was 79. Let's look at 87. And 87 says to find the relative extrema, points of inflection, and then use a graphing utility to confirm our results. So x squared over 2 minus ln of x. So my domain here has to be x greater than 0. Y prime is 2x over 2 minus 1 over x is x minus 1 over x, or x squared minus 1 over x. So I have y prime is x plus 1, x minus 1 over x. And it would appear that I would have critical numbers at -1 and 1, but I don't have any graph over here to the left of 0, which is my vertical asymptote, so that's not a critical number. The only critical number is at 1. And when I have a number between 0 and 1, this is a positive and a negative and a positive, so that's negative and decreasing. And then to the right of 1 is positive, positive, and positive, which is positive and increasing. My second derivative here is 1 plus 1 over x squared is x squared plus 1 over x squared, and I have no points of inflection here since there's no zeros of my second derivative. So this is always going to be concave up on its entire domain, and this is going to be decreasing on 0 to 1 and then increasing from 1 to infinity. And local min at 1 and then 1/2 minus 0, that's going to be 1/2 at 1 1/2. Let's verify this with the calculator now. So y equals, it's clear and clear. And this is x squared divided by 2 minus ln of x. I want to graph, and I want to see that it's decreasing from 0 to 1 and then increasing from 1 to infinity. And I want to find this minimum point here that should be right over here, right about there. And that's at 1/1/2. So we're good. And the concavity is concave up always, no point of inflection. Let's look at 89. And this will be our last one for this video. Y is equal to x ln of x. So y prime be equal to, this is u times v with u equal to x. V equal to ln of x. U prime is 1, v prime is 1 over x. U prime v plus v prime u. Y prime is 1 times ln of x plus 1 over x times x. So y prime is ln of x plus 1. If I set that equal to 0, then ln of x is equal to -1. X is equal to e to the -1st, or 1 over e. And I have a domain here of x greater than 0. So that critical number is in my domain. 1 over e. And let's look at what e to the -1st is. Okay, so I could pick something like 1/4 as a test point here, and something like 1 as a test point up here. I'll be okay. So ln of 0.25 plus 1 is a negative value. That makes this part decreasing. Ln of 1 is 0, 0 plus 1 is 1. That's positive and increasing. Second derivative is 1 over x, and that will be, so this is f prime, this is 0 to infinity, and no points of inflection for that, because it never changes sign within its domain. And all the numbers greater than 0 are going to give me a positive value. It'll be concave up on 0 to infinity. This will be decreasing from 0 to 1 over e, and will be increasing from 1 over e to infinity. Let's check this with the calculator. And again, 1 over e is about 0.36788. Just when I look for that for anything coming up here with the calculator, since it's not going to show me an exact value with e. So y is equal to x times ln of x. And let's graph this. And it is, there's a low point right there. It's hard to see, but it is there. and the minimum is at 1 over e, and the y value is also 1 over e. I should stick this in. Y equals 1 over e times ln of e to the negative first. So it's going to actually be negative 1 over e for the y value. So local min is 1 over e, negative 1 over e, and then no point of inflection for me to find. All right, a little bit longer video, especially since I did those two proofs. So sorry, this one went a little long. We will come back next time and talk about section 5.4, suggested homework problems. So see you for the next video.